Our presentation is titled Improving Centrifugal Compressor Performance by Optimizing the Design of Impeller Using Genetic Algorithm and Computational Fluid Dynamic Method. This project focuses on applying a hybrid simulation and algorithm approach to enhance compressor efficiency and stability. And we are the group Firestorm, and our team consists of 4 members, which is Pan Chuan, which is me, and then Yuzu Ming, Wei, and Hua Lun Shen. Okay, together we work to develop a method that combines advanced computational tool with engineering insight to solve a real-world turbomachinery problem, which actually we are only extracting from the article. Let's begin by understanding the role and importance of a centrifugal compressor in the industry. Firstly, we will have the Hua Lun Shen do the introduction first.
Introduction. The centrifugal compressors are dynamic machines used in HVAC systems, gas turbine, turbochargers, and various industrial processes. They work by accelerating the air or gas with a high-speed impeller, then converting that velocity into pressure through a diffuser. The impeller is the core component. Its rotating blades force fluid outwards via centrifugal force, driving compression, improving the compressor performance is critical. These units consume significant energy. Even small efficiency gains can reduce operational costs and emissions. Given their widespread and continuous use, optimizing them contributes meaningfully to industrial sustainability. This presentation explores how advanced optimization techniques, by combining genetic algorithm and CFD, can improve the impeller performance and overall compressor efficiency. There are 2 main strategies for improving the centrifugal compressor design. The first one is the trimming method. This involves manually adjusting the blade shape. It's simple and low cost, but limited in scope and prone to designer bias. The second one is the automated optimization method. This uses an algorithm like the genetic algorithm to explore a wide range of blade geometry. It supports a multi-parameter optimization, offering a more significant performance improvement. While computationally heavier, it eliminates the guesswork and finds solutions that are often beyond human intuition. The genetic algorithm used by this study is inspired by the principles of natural selection. It begins with a population of impeller design and evaluates their fitness based on the aerodynamic performance, particularly the isentropic efficiency and the pressure ratio. The best performing designs are selected, recombined, and mutated to form the next generation. This iterative process enables the algorithm to converge on the optimized blade geometries over successive generations. It is particularly effective for high-dimensional design space with complex independencies. CFD, or computational fluid dynamics, plays a pivotal role in evaluating the aerodynamic performance of each impeller design. The ANSYS CFX solver is employed due to its robustness in handling the rotary machine, especially centrifugal compressor. It solved the Reynolds average Navier-Stokes equation by using the SST turbulence model, capturing the adverse pressure gradient and separation phenomena accurately. This simulation provides pressure field, velocity distribution, and energy loss data. These are crucial inputs for the general algorithm to make informed design decisions. The optimization focuses on 2 major variables. The first one is the starting point of the splitter blade at the hub, midspan, and the tip. This is followed by the second, which is the angular orientation of this splitter blade relative to the main blade. These parameters critically affect flow direction, streamline attachment, and local incidence angle. By adjusting this feature, the algorithm can significantly reduce energy losses associated with the flow separation and mismatched blade angles.
The first step in the optimization workflow is the interpretation of blade geometry. This begins with the definition of blade profile using key control points. These points determine the curvature and length of the blade across the impeller radius at the hub, midspan, and tip. By using interpolation techniques, we can construct a continuous and smooth 3D surface that defines the blade shape. This approach provides parametric flexibility, enabling the genetic algorithm to easily adjust and regenerate blade geometries across successive generations. This also ensures geometric consistency and compatibility with the downstream meshing and simulation tools. Once the geometry is defined, the next step is 3D modeling using BrakeGen, a specialized turbomachinery design tool in the ANSYS suite. BrakeGen allows for precise control over blade features such as thread length, blade count, curvature, and thickness. It also ensures that critical geometry transition between the hub and stroke is accurately modeled. For centrifugal compressor, this step is essential as it allows uh, us to stimulate real-world curvature effects and rotational behavior with high fidelity. The output from BrakeGen is a complete solid model of the impeller ready for meshing and stimulation. Step 3 involves meshing the 3D impeller geometry using TurboGrid, a meshing tool specifically developed to the turbomachinery application. The mesh quality is crucial for accurate CFD result in the case. We generate a high-resolution structure mesh using over 1.25 million nodes. Special attention was given to the boundary layers, maintaining a Y plus value below 30 to ensure sufficient resolution of near-wall flows. TurboGrid also creates mesh block that align with blade curvature, improving flow fidelity across pressure and suction surface. This step ensure numerical stability and reliable turbulence modeling. With the mesh complete, the simulation is conducted in NCCFX. The model simulates steady state flow through the rotating impeller domain using the Reynolds average Navier-Stokes equations. Key boundary conditions applied include inlet total pressure and temperature of 101 kPa and 288 Kelvin, respectively. The mass flow rate at the outlet set at 0.28 kg per second and rotational speed fixed at 92,000 rotations per minute. The turbulence is modeled using the shear stress transport model, which combines the K omega and K epsilon models to handle both near-wall and free strain regions. This stage provides critical outputs such as velocity fields, static and total pressures, turbulent intensity, and isentropic efficiency, all of which are passed to the genetic algorithm for evaluation. In the final step, the CFD performance results such as efficiency and pressure ratio are used as input for the genetic algorithm. The genetic algorithm evaluates each redesign fitness, selects the best performing candidates, and generates new variations through crossover and mutation. These update geometries re-enter the workflow in a closed-loop process that continues until performance improvement plateau. This iterative approach enables automated refinement of the impeller design based on real-world aerodynamic data.
Now we continue with the base compressor specifications. The base design is derived from standard GT4082 turbocharger. It consists of 6 main blades and 6 splitter blades, operating at 92,000 RPM with a design mass flow rate of 0.28 kg per second. The nominal pressure ratio is 2.28 and its initial isentropic efficiency is 78%. No inlet vent is used, and the impeller has radially oriented leading edges. This configuration serves as the benchmark for evaluating the optimization gains. Now we continue with the result of optimization. First of all, the efficiency improvement. To, to optimize impeller design resulted in the approximate 2% improvement in maximum isentropic efficiency. Notably, this enhancement was most pronounced at a higher mass flow rate, indicating that the new design offers better aerodynamic behavior under high load conditions. This is a substantial gain in turbomachinery context, where even sub-percent improvements are highly valuable due to their cumulative energy saving across large installations. Then is the pressure ratio stability. Despite the geometry modifications introduced by the algorithm, the pressure ratio remained nearly constant. Note
The drop observed was only 0.02%, which is negligible. This result confirmed that the design changes enhance aerodynamic efficiency without sacrificing the compressor's ability to perform pressure work. Now is the flow field enhancement. The optimized design demonstrate substantial improvement in flow uniformity and separation control. Flow separation was mitigated near the hub and slope region, while the incident angles at the splitter blades were reduced. This translates to smoother energy transfer, reduced turbulence generation, and more stable operating characteristic under varied load condition. For the surge and choke behavior, one of the most notable results was the 7% delay in the one set of surge. This suggests an increased margin of stable operation, especially at full and low flow rates. Although the choke characteristic remain mostly unchanged due to geometrical constraint at the throat, the shock wave structure near the slope was better managed, contributing to a more robust high-speed operating envelope. Now we continue with the analysis of flow field. First is the hub analysis. In the hub region, the base design suffered from mid-blade flow detachment. The optimized impeller shortened the hub side splitter's bed, which reduced the effective incident and prevent flow separation. Now is the slope region. As at the slope, the velocity field show reduced secondary flow and less turbulence, resulting in higher aerodynamic stability. These improvements confirm the subtle geometric adjustment can yield significant change in flow clarity. And the last is the Mach number distribution. The high Mach region near the slope persists persisted in both designs. However, the optimized impeller redistributed flow more effectively. As a result, shock strength and flow unsteadiness were minimized, especially near the trailing edge. This suggests the design is better equipped to handle high speed flow without premature choking or stall.
Now it's my turn to talk about the validation of the simulation. After they done all the simulation, we have to say how valid is it? How is it true? And what has happened? So to ensure the credibility of our simulation framework, the CFD result will compare against the experimental data. So you can see at the graph the maximum deviation observed was 4.2%, which fall well within an acceptable limit for the turbomachinery simulation. This validation support the reliability of the aerodynamic improvement predict in the study. So it's definitely that it's reliable. According to this CFD prediction, only have a maximum error of about 4.2%. So now I go to the conclusion. For the conclusion, this study actually proposed that a hybrid optimization method combining a genetic algorithm with CFD simulation to improve a centrifugal compressor performance, starting with a base turbocharger design. We generate and evaluate multiple impeller variants. The result was a 2% gain in the isentropic efficiency and a 7% improvement in the surge of stability, and also achieved without compromising the pressure ratio. So this outcome show that automated simulation-based optimization is both effective and practical. So overall, I think that this method demonstrates a high potential for advancing the compressor design and supporting the sustainability sustainable engineering development through a data-driven innovation. So it is confident that CFDGA is a reliable tool for the sustainable compressor and development. So now we goes to the future work, right? So for the future work, building on the research, future work will aim to expand the optimizer beyond the impeller, covering the full compressor stage such as the diffuser, volume, and return system. So experimental testing is another key next to step to validate the CFD prediction, confirm the real world performance, right? So that also a potential to integrate a machine learning into this workflow. So it can reduce the simulation time and also enhance the prediction accuracy. So lastly, by applying the multi-objective optimization can help balance the aerodynamic efficiency with a structural stress, acoustic performance, and environmental impact. So moving toward more sustainable and more practical compressor design. All right, thank you. I think that's all from our presentation for this